Hey guys, welcome back to a new video. In this session, we'll be tackling exercises on how to solve integrals using the method of partial fractions. Specifically, it is the go-to method when you have to solve an integral of a fraction of polynomials. It is traditionally a topic which a lot of students struggle with, which is why we will solve 3 exercises step by step to avoid any confusion or misunderstanding. In particular, the last exercise will be quite challenging. However, if you understand how to solve that one, you can be sure that you can solve any exercise using this method of partial fractions. As always, the timestamps of the exercises can be found in the comment section below, and if you have any questions, let me know in the comments below. And with the intro out of the way, let's get into it. The first exercise will be the most basic integral where using the method of partial fractions makes sense. And it's the perfect opportunity to get familiar with how to solve these integrals. It's the integral of x squared plus 5x minus 8 divided by x squared minus x minus 2 dx. The very first step that we'll have to do in all of these exercises is to check whether the degree of the polynomial in the enumerator is larger or equal to the degree of the polynomial in the denominator. And if this is so, then we first have to perform a long division in order to make the degree of the polynomial in the denominator the largest one. In this case, we see that the degree in the enumerator is 2, because we have an x squared here. In the denominator, we also have 2, since we also have an x squared in the denominator as being the largest power of 2. Because they're equal, we first have to perform a long division. And if you're not familiar with how to perform long division of fractions, then I highly recommend that you watch my video where I go step by step through exercises on long division. First, we divide this term with this term, and we get our result 1. Then we multiply this 1 with each term of the polynomial right here. And we write the result beneath this polynomial. So we get 1 times x squared, which is of course x squared. 1 times minus x is minus x. And 1 times minus 2 is of course minus 2. And then we subtract these two polynomials from each other and we'll get the result 0 plus 6x minus 6. And thus our result is 1. And our rest term is 6x minus 6. So we have found that x squared plus 5 times x minus 8 divided by x squared minus x minus 2, our original fraction, is equal to 1, which is our result here, plus our rest term, which is 6 times x minus 6, divided by our original denominator, which is x squared minus x minus 2. And what we've done now is we've written our integral as the sum of 2 integrals. And we see that the first integral here is a very easy one to solve. And so we're left with solving the integral of this reduced fraction. So we can rewrite the integral that we have to solve as being the integral of 1 dx, which of course we know is simply x, plus the integral of this fraction, which is 6 times x minus 1 divided by x squared minus x minus 2 dx. And now we see that in the fraction that we're left with, the degree of the enumerator, which is 1 in this case, is indeed lower than the degree in the denominator, which is of course 2. And now we can go to the second step, which is to write our denominator, our polynomial in the denominator, as a product of 2 terms. And we see that we have a second order degree polynomial in the denominator. And to be able to write this as something x minus something times x minus something else, we need to find the 0 points of our second degree polynomial. Because if we found these, then we know that we can always write our second degree polynomial as a product of 2 terms. So what we have to solve is x squared minus x minus 2 is equal to 0. And we know, of course, that this equation has 2 solutions, x plus minus, which is equal to 1 plus or minus the square root of 1 squared minus 4 times 1 times minus 2. divided by 2. And if you're not entirely sure how I got this, I can refer you to my video on how to solve quadratic equations. We can rewrite this as being 1 plus minus the square root of 1 plus 8 divided by 2, which is of course 1 plus minus 3 divided by 2. So we get two solutions here. If we take the plus sign, we get 1 plus 3 divided by 2 is 4 divided by 2 is of course 2. If we take the minus sign, we get 1 minus 3, which is minus 2, divided by 2, and we get minus 1. So now we know that we can write this second order equation, or this second order polynomial, as being x minus this first 0 point, so x minus 2, times x minus the second 0 point, which is minus 1. So minus and minus becomes a plus, and we get 1. And this is how we can write our second order polynomial. So this is how we can write our fraction. So again, now we've rewritten our integral as this 1 dx, just we copy this, plus 6 times, because 6 is a constant, so we can pull it outside of the integral, x minus 1 divided by x minus 2 times x plus 1 dx, which is the result of our second step in our algorithm to solve our initial integral. So what we're left with is trying to solve this integral. And this brings us to the third step, which is to how to actually now solve this integral. We want to write our fraction, so our x minus 1 divided by x minus 2 times x plus 1. We want to write it as a sum of two fractions, where the first fraction has as the denominator our first term of the product here, and the second fraction has in the denominator our second term here, so x plus 1. So what comes in the numerator of these two fractions such that this equality sign holds? Well, that is exactly what we're trying to figure out in this third step. We first write it as a and b, and of course, simply writing it doesn't solve it. We now need to solve for a and b. So we try to find a numeric value for a and b. To get this numeric value, we first rewrite this sum of two fractions as a single fraction. To do this, of course, we multiply this a with this denominator, and then we multiply b with the other denominator. So we get x plus 1 times a plus x minus 2 times b. And the denominator then becomes the product of these two denominators. And this step to this step is simply writing the sum of two fractions as a single fraction. The next step is to gather all of the terms with x in the enumerator together. So we have a times x here. So we have an a, and we have a b times x here. So we have plus b. Then we take all the terms together which do not have an x, which is a plus a here and a minus 2b here. So we have plus a minus 2b. And the denominator we just copy as x minus 2 times x plus 1. What we do now is that we compare the fraction that we've obtained here with the fraction that we originally started with. And we see that both denominators are equal to each other. However, the enumerators are quite different. But if the denominators of two fractions are equal to each other, and the fractions as a whole are equal to each other, then that means that the enumerators will have to be equal to each other. And in our original fraction, we see that we basically have 1 times x minus 1. And if we compare all the terms with an x, we see that 1 then has to be equal to a plus b. And likewise, we see that we have a minus 1 in the original fraction, and we have in here plus a minus 2b. So the a minus 2b will have to be equal to minus 1. This means that we get two equations that we have to solve. We have 1 is equal to a plus b, and we get that minus 1 has to be equal to a minus 2b. And these two equations have to be true simultaneously, which gives us a system of two equations which we already know how to solve. And if you don't, again, I have a video specifically dedicated to this topic where I go through exercises on how to solve the system of two equations. We first rewrite this second equation and we get that a is equal to 2b minus 1. And then this a, we simply fill in here in this a in the first equation. So we get 1 is equal to 2b minus 1, which is this a, plus b. And from this equation, we directly see that 2 is equal to 3 times b, or b is equal to 2/3. And we already have our first result here. Now if we fill this b into our second equation here, we get that a is equal to 2 times 2/3 minus 1, which gives that a is equal to 1/3. And we have found our a and b such that we can write our initial fraction, which was a single fraction with a product in the denominator, as a sum of two fractions. And we've now found a to be 1/3 and b to be 2/3. So we can rewrite our initial fraction as being the following. We have 1/3 divided by x minus 2 plus 2/3 divided by x plus 1. And this is now the fraction that we originally had. Let's go back to the integral that we had to solve. We have this integral that we had to solve, and we had this fraction, which we now have rewritten as the sum of these two fractions. So we get that we have to solve the integral of 1 times dx, which we just copy, plus 6 times the integral of 1/3 divided by x minus 2 dx, plus 6 times the integral of 2/3 divided by x plus 1 dx. And at this point, we've completed all of these steps that are necessary to rewrite our original integral that we had to solve, so this integral, and we've rewritten it as a sum of integrals of which we already know how to solve them. So let's now do the final step and solve our integral. So our first integral here, which is the integral of 1 dx, is of course simply x, because if we derive x, we get 1 again. Then the second integral here, we pull out the 1/3 in front of it. So we get the integral of 1 over x minus 2 dx. And the same we do for our third integral here. We pull out in front the 2/3 to get 6 times 2/3 times the integral of 1 over x plus 1 dx. Solving this even further, we get x plus 2 times, and what we're left with is an integral which can be easily solved by using substitution. We can simply write this as the integral of 1 over x minus 2 times d of x minus 2, because d of minus 2 always drops out, plus 4 times the integral, again here, we can write this as an integral with substitution of dx plus 1. And what we see now is that we have two integrals of the form of 1 over u du, which is of course the ln of u plus a constant. And we get our result, x plus 2 times the logarithm of x minus 2 plus 4 times the logarithm of x plus 1 plus a constant c, because we're doing indefinite integrals. And this is our final solution for the integral that we had, which was the integral of x squared plus 5 times x minus 8 divided by x squared minus x minus 2 dx. And again, we got this solution by going through a fixed number of steps where we try to rewrite our initial fraction in more comprehensive ways. Let's go to the next exercise and have some more practice. So we have the integral of x to the power of 3 minus 2x squared minus x plus 3 divided by x minus 2 squared dx. And this is our original integral. Again, the first step is to check the degree of the polynomial in the numerator and in the denominator. In the enumerator, the highest power of x is 3, so the degree of the polynomial is 3. In the denominator, we have the highest power of x being 2, so the degree of the polynomial in the denominator is 2. And we see that 3 is larger than 2, so before we do anything else, we have to perform a long division. We get x to the power of 3 minus 2x squared minus x plus 3 divided by x squared minus 4x plus 4, which is simply written this x minus 2 squared out. So we divide x to the power of 3 by x to the power of 2, and we get, of course, x. Then we multiply this x with each of these three terms, and we get x to the power of 3 minus 4x squared plus 4x. And we subtract these two polynomials to get 0 plus 2x squared minus 5x plus 3. And we're not done at this point, because now we can still divide this 2x squared by this x squared here. And we get as a result, of course, being 2. Then we again multiply this 2 with each of these three terms, and we get 2x squared minus 8x plus 8. And again, we subtract these two polynomials to get 0 plus 3x minus 5. And this will be our result of our long division, and this will be the rest term, which means that we have now rewritten our initial fraction as the following: x plus 2 plus 3x minus 5 divided by our original denominator. And of course, this means that also our integral is now rewritten as this integral, of which we of course know the integral of these first two terms. So in the second step, we first rewrite what we now have. We have the integral of x plus 2 dx, which is this part, plus the integral of the fraction that remains. So 3x minus 5 divided by x minus 2 squared dx. And as I said, this integral will leave as it is right now because we already know what it's going to be, and we focus on this integral. And again, we want to rewrite the fraction that we're left with now as a sum of two fractions. And because we have now this complete square in the original denominator of our fraction, the denominator of each of the two fractions will be the following. So we have x minus 2 as the denominator of the first fraction, and x minus 2 squared as the denominator of the second fraction. And again, this is only the case when we have this complete square in the denominator of our original fraction. So what we do is, again, we write a and b, and of course a and b is now what we are trying to find. So we again write this sum as two fractions as being one fraction with one denominator. So we multiply this x minus 2 squared with a. So we have a times x minus 2 squared plus this denominator times b, which is of course b times x minus 2. And our denominator will simply become x minus 2 to the power of 3, simply the product of these two denominators. What we can immediately see is that we can cancel out 1 power of x minus 2. So we can rewrite this as being a times x minus 2 plus b divided by x minus 2 squared. And what we do now again, we rewrite this by gathering all of the terms with an x and all of the terms without an x. The terms with an x will be a times x, because only this a is multiplied with an x. And the terms without an x will be b minus 2a. And we rewrite our denominator as it was. At this point, we again compare this fraction with this fraction, because there's an equality sign between these two, and we know that the denominators of both fractions are equal. We know that the enumerators have to be equal. So we see that the coefficient in front of the x will have to be 3. So we get that a is equal to 3. Again, we see the term without an x has to be equal to minus 5. So b minus 2a has to be minus 5. And we are again left with this system of two equations, which we know how to solve and is significantly easier than the previous one because we already know that a is equal to 3. So we just copy a is equal to 3 and now fill it in our second equation. So that's 2 times 3 is equal to minus 5. Rewriting this equation, we get that b is equal to 1. And we have our two solutions, a is equal to 3 and b is equal to 1, which can be directly filled in the sum of the two fractions that we wanted to rewrite our original fraction in. So we get that our original fraction can be written as 3 divided by x minus 2 plus 1 divided by x minus 2 squared. And now we can also rewrite the integral that we have to solve. So we had the integral of x plus 2 dx, which we just copy and leave for later to solve because it's very easy to solve this one. Then we had the integral of our original fraction, which was 3x minus 5 divided by x minus 2 squared dx. And what we found now is that we can rewrite this as being the integral of x plus 2 dx plus 3 times the integral of 1 over x minus 2 dx, which is this term, plus the integral of 1 over x minus 2 squared dx, which is of course this term. And now we are left with 3 integrals of which we already know how to solve them. So the most difficult part is over now. We've reduced our initial integral of a fraction of two polynomials as 3 integrals which are very basic and we know how to solve. So we get the following integrals. The integral of x plus 2 dx is of course x plus 2 squared, which is a very easy substitution to make. What we then get is 3 times, again, the logarithm of x minus 2, because this is again an integral where we can use substitution to get 1 over u du and integrate it, which is of course the logarithm of u. And what we then get is a new integral. However, this is quite easy to solve because if we write dx minus 2, because we can always write minus or plus a constant of this differential, and we divide by x minus 2 squared, then we see that this integral simply becomes the integral of 1 over u squared du, which is of course simply 1 over u. So we can rewrite this again, and let me write this in green because this is our result, x plus 2 squared plus 3 times the logarithm of x minus 2 plus 1 over x minus 2 plus this constant c. And this is our final result for the initial integral that we had. Let me rewrite it. X to the power of 3 minus 2x squared minus x plus 3 divided by x minus 2 squared dx. Let's now go to the final and most complex exercise. We've got the integral of 4x squared plus 11x plus 15 divided by x to the power of 3 plus 3x squared plus x minus 5 dx. And this is quite daunting looking. However, if we just repeat the same steps as we did in the previous exercises, we can be sure to get the right result. Again, the first step is to check the degree of the polynomial in the numerator and the denominator. We see that we now have 2 for the highest power of x in the numerator and 3 for the highest power of x in the denominator. So we know that we don't have to use a long division at this point. However, what we do want to do is try to factorize this denominator polynomial. We try to write it as a product of polynomials of a lower degree. And this basically boils down to finding the zeros of this equation. And finding the zeros of a third order polynomial equation can be quite difficult. However, it's always a good thing to first simply try a few values. For example, x is plus 1 and x is minus 1. Let's fill in x is plus 1. What we get if we fill in 1, we get 1 plus 3 plus 1, which is 5. minus 5, which is indeed 0. So we are lucky here and we get that this is indeed a 0 point of the equation. Having found this first 0 point, we can rewrite our third order polynomial as a product of x minus 1, since 1 is a 0 point of our polynomial, and a second degree polynomial. Now, what will this second degree polynomial be? Well, we can simply find this out in the following way. We know that we have 1 times x to the power of 3 in our original polynomial. This means that in front of the x squared of our new second order polynomial will also be 1, because we'll get x times x squared, which is indeed x to the power of 3. Then we have minus x squared if we multiply these two terms. However, in our original polynomial, we have 3 times x squared. So what we still need is plus 4x, since if we multiply our x with this plus 4x, we get 4 times x squared. And we multiply minus x with x squared, we get minus x squared. And 4 times x squared minus 1x squared is indeed 3 times x squared. And for the final term, we simply note that we have a minus 5 here and we have a minus 1 here. So the only way to get minus 5 by multiplying minus 1 with a specific number is if this specific number is of course 5. And this is how we rewrite our original third order polynomial as a product between a first order polynomial and a second order polynomial. A next step would be to write this second order polynomial also as a product between two first order polynomials. This means finding the 0 point of this second degree polynomial. This can be done by simply looking for the solutions minus 4 plus minus the square root of 4 squared, which is 16, minus 4 times 1 times 5 divided by 2 times 1, which is 2. And we see here that the number inside of the square root is smaller than 0, which we cannot solve if we don't allow for complex numbers. So this second order polynomial here does not have any real solutions, so no more 0 points. And we'll just have to stick with this form right here. So to now rewrite our integral, we get 4x squared plus 11x plus 15 divided by x minus 1 times x squared plus 4x plus 5 dx. Which brings us to the second step, which is to rewrite our original fraction, which is a fraction with a product of two polynomials in the denominator, as the sum of two fractions. So we have 4 times x squared plus 11x plus 15 divided by x minus 1 times x squared plus 4x plus 5. So we want to rewrite this as a sum of two fractions within the denominator of the first fraction, x minus 1, and in the denominator of the second fraction, we have x squared plus 4x plus 5. So this is what we want to have in both of the denominators of the sum of our fractions. In the enumerator, here again we have a, just the number that we're trying to find. However, in the second fraction, because we have a second order polynomial in this denominator, which simply comes because we have a second order polynomial in our original denominator, what we want to find in our enumerator is b times x plus c. And note that we now not simply have a number, for example, b, but we have a term with an extra x here, which is because we have a second order polynomial in the denominator. As the second step, we write this as one fraction, x minus 1, multiplied with x squared plus 4x plus 5. So we get this denominator times this enumerator. So we get a times x squared plus 4x plus 5 plus this denominator times this enumerator. So we get bx plus c times x minus 1. The next step, as always, is to gather terms with equal powers of x. Let's first take x squared. So we have a times x squared here, and we have b times x multiplied with x, which is b times x squared. So we get a plus b times x squared. And now we take all the terms with a single power of x. So we have a times 4x. So we already have 4a. Here we have minus 1 times b times x. So that's minus b. But we also have c times x. So we also get a c. So plus c. And all these are multiplied with x. And to end off, we look at the terms without any x. So we have a times 5. So that would be 5a. And here we only have c times minus 1, which become minus c. And of course, we still divide by our denominator, which is x minus 1 times x squared plus 4x plus 5. And again, we've come to the point where we can directly compare the two fractions that we have, our original fraction and the fraction which will give us a, b, and c. The coefficients with x squared. We find that a plus b has to be equal to 4. Then the coefficients with an x, which is this long bracket here, we have 4a minus b plus c is equal to 11. And then of course we are left with the coefficients without an x. So that would be 15 here and 5a minus c here. So we get that 5a minus c is equal to 15. And instead of having a system of 2 equations here, we get a system of 3 equations, on which I also made a detailed video and we can now readily solve. So we get that b is equal to 4 minus a from the first equation. We get that c is equal to 5a minus 15 from the last equation. And now we can use these two expressions to fill in our second equation. So we get 4 times a minus 4 plus a plus 5 times a minus 15 is equal to 11. And this equation directly gives us that a is equal to 3. And a is equal to 3 directly gives us an expression for b, because we have that b is equal to 4 minus a. So we get that b is equal to 1. And a is equal to 3 can also be directly filled in this equation. So we get that c is equal to 0. And these results can be directly filled in the sum of the two fractions that we want. So we can fill in a is equal to 3, b is equal to 1, and c is equal to 0. And this gives us that our original fraction decomposes in the sum of the following fractions. We have 3 divided by x minus 1 plus x divided by x squared plus 4x plus 5. And again, how do I get these two fractions? These are simply these two fractions with a is equal to 3, b is equal to 1, and don't forget this x here, and c is equal to 0, which is of course equal to our original fraction in our original integral. So what we're left with is to solve these two integrals, and we are done. Solving this integral should be clear by now. This simply becomes this integral of 1 over u du, and this simply becomes the ln of the absolute values of x minus 1 times 3, since this 3 can be put outside of the integral. Let's now look at this integral, which is a bit more complex to solve. What we will first try to do is make of the numerator the derivative of the denominator, because we know that the integral where the numerator is the derivative of the denominator is a basic integral which is simply the logarithm of the denominator. So we can do this by simply writing what we want, so 2x plus 4 divided by x squared plus 4x plus 5, since 2x plus 4 is the derivative of this denominator. However, we cannot put an equality sign between these two fractions yet, because we just written what we wanted, 2x plus 4, whereas we simply have 1x. So what we do then is we simply write this as 1 over 2 times 2x plus 4, because then we simply get this x again without the factor of 2. However, then we are still left with 1/2 times 4, which is 2, and this 2 is not appearing over here. So to compensate for this, we have to subtract with 2. And now we can use an equality sign between these two fractions, because if we just simply recalculate this, we get 1/2 times 2x plus 4 minus 2. We get, of course, x plus 2 minus 2, which is, of course, x. And x is indeed what we had in the numerator in our original fraction. However, now we are left with two integrals again, of which one integral has the derivative of the denominator. So we can rewrite this as being 1/2 times the integral of 2x plus 4 divided by x squared plus 4x plus 5 dx. And don't forget this minus 2 here. So we have minus 2 times the integral of 1/x squared plus 4x plus 5 dx, which is equal to, like I said, this integral can be easily solved because the numerator is the derivative of the denominator. So this will be 1/2 times the logarithm of the denominator, x squared plus 4x plus 5, minus 2 times the integral of 1/x squared plus 4x plus 5 dx. So again, this integral is now solved, and now we are left with only one integral to solve before we are completely done. Again, because we've solved this integral to be this solution, we've solved this integral to be this solution, so now we're only left with solving this integral. So let me rewrite our complete solution, which is 3 times the ln of x minus 1, which was, of course, this first integral, which we solved directly. Now we have plus 1/2 times the logarithm of x squared plus 4x plus 5, which was part of this integral, which we split into two integrals here and solved the first integral. And now we are left with minus 2 times the integral of 1/x squared plus 4x plus 5 dx. And how we will solve this integral now is to try to rewrite it in the form of 1/x squared plus 1 dx, because this integral we know to be the arctangent of x. So how do we now write this denominator as x squared plus 1, or better said, something squared plus 1? To do this, we use a trick called completing the square. Let's look at the denominator. So we have x squared plus 4x plus 5. And we see that we can tear this 5 up into two parts. So we simply write 5 as plus 4 plus 1, which is still 5, right? However, at this point, we have this term right here, x squared plus 4x plus 4, which is simply x plus 2 square, right? If we calculate these brackets x plus 2 squared, we exactly get x squared plus 2x plus 4. So this means that we've rewritten our integral as being 1/x plus 2 squared plus 1. And now this already looks a lot like this form right here, 1 over something squared plus 1. And at this point, we use, of course, the substitution method, because we can always write this dx as being d of x plus or minus some number. In this case, we write it as d of x plus 2. And we see that we have now 1 divided by something squared d something, which is simply the arctangent of that something. So this will be equal to the arctangent of x plus 2. And this means that we finally solved our integral. And the final solution is equal to 3 times the ln of x minus 1, which is this term here, plus 1/2 times the ln of x squared plus 4x plus 5, minus 2, which we should not forget, this coefficient in front of our integral, and the integral that we just solved to be the arctangent of x plus 2. And this is our final integral, which took quite some time to solve, but we got right either way. And this brings us to the end of this video, and I hope that you are now more familiar with how to solve integrals using the method of partial fractions. If you have any questions or are confused about anything, please let me know in the comments below and I'll be sure to answer them. If you liked the video, meaning if you learned something, give it a thumbs up, and if you want to get notified by future releases, consider subscribing. And with that, I thank you very much for watching, and I will see you guys in the next one. Bye.